All right, so the plan today. We are going to go back through the Data Locality chapter, but this time implement the exercises in Rust. Or I guess it's more like examples. There's not really any exercises in the book. But let's go down and find the first one here. Right, so this is like the sleep one. We didn't really do that because that's just like simple as an example of like what's happening. Here it is, our first real code example here. So we have our class game entity, and then we have this constructor on it. So let's go ahead and open up here. And I'm gonna turn on the line highlighter. So if you want to highlight any lines to sort of ask questions, you can use bang line and then the number. All right, so let's do struct game entity. And then this has us, looks like we're gonna be storing internally AI, physics, and render. So that means we're gonna need struct, I guess I'm gonna do this afterwards. Struct AI. Now they're calling this an AI component. So struct physics component, struct render component. And then we're going to store these like instances of these in here. So we're going to have the AI, which is AI component, physics, which is physics component, and render, which is render component. Now here it looks like they have pointers or references, but we're not going to do that here. I don't want to have to set up lifetimes in the structs. So I'm going to give them ownership to their own specific AI. So each game entity gets its own AI. And it controls when it goes in and out of scope and when it dies, essentially. Now, this is a constructor. So to implement that, we'll implement game entity, hub function new. And this is, we're taking in an AI, which is an AI component. We're taking in physics, which is a physics component, and render, which is a render component. We're saying that we're returning a game entity, and here we're going to say game entity and AI physics render. And there we go. So that is now returning these. So we can now set up in our, you can basically say in main that we're going to switch this between like, okay, we have setup, and then we're going to have our main game loop. They're also having getters for these to return them. So that's a choice. We could also just make these public. That would make them writable. If I don't want them writable, definitely having like the lens in of like getting them would be necessary. So if I want to like do this example exactly as it is, that being said, I think just making them public would be good enough. And then this is what these other these all look like. They have update methods on them, and that's it. So we're going to implement whatever you are. So we're going to say pub function update. we're going to take in mute self just in case it needs it. We're not going to like take in anything else. We're not going to return anything. And then we're just going to say, like, do the update code here. And so now we're going to be okay, so now we're going to have a vector essentially of now they say pointers, but it really should just be like a vector of the actual everything like that we're doing, all these entities. So in here in setup, we're going to do let entities equals and it's going to be a vector of, and we're going to put in game entities, which of course means we need these like AI physics and render too. So if I do this multi-line, so let's add 3 in here. So we're going to do game entity new and then AI component. So AI component like that. Physics component, render component. So if I take this entire line, in fact, I can just go to the end, add a comma, copy a few times. Actually, trailing commas are fine here. I think they are, at least in, oh, I don't know if they're okay in vectors. We'll find out. And semicolon U. All right, so now we have our 3 entities. Interesting that this one has green on it and these do not. What's different? Okay, well, anyways, Rust Analyzer or, yeah, Rust Analyzer, I think wants the comma there, so I guess we're gonna add that in. All right, so I don't know why the coloring is a little bit weird, but we have our entities, and so now we're gonna have our the entire loop through here. So we're gonna also have that game over equals false. We'll have to have some method of like determining when this becomes true. So we will loop just do a forever loop and then break as soon as game over happens. We also can do a while loop. There are while loops here. So while not game over, then do all of these. So we're gonna loop through 3 times each, like the game entities, and then run, like, you know, for the first one, run the AI updates, then run the physics updates, and then run the render updates. And there's a few different ways we can do this. With Rust, because it's compiling down to be as fast as possible, I don't even know if it matters that we choose a normal for loop or one of the iterator methods like that we get off of vectors for free. So we might be able to do entities dot, is there a for each? I don't think there is. So I don't need to map it or anything, so I guess probably just a for loop then. For entity in, and this one we can get a reference. So this is going to have to be a mutable reference because they need mutable abilities up here. So for entity in mutable entities, that gives us a mutable game entity, and so entity dot update. Entity dot AI dot update. Now you're upset Cannot borrow entities as mutable, as is not declared as mutable. Okay, so all of these need to be mutable here. So entities, you are mutable. All right, so we're fine there. Just a guy here. Hello, good morning. And then we're going to repeat this 3 times. And this time for the physics, and this time for the render. And that gives us, okay, so we're updating the AI, we're updating the physics, and we're updating the rendering stuff. What project am I up to? I am working on the game programming patterns, and I am converting the Data Locality chapter to Rust. This is exactly... Oh, this is now we've broken these out into different components here. It's not in the game entities anymore, right? Yeah, okay. So now the idea is that we're breaking these, like the AI, up into separate different components. So we have like AI component, physics component, render component. And so instead of this mute entities like this, for example, we would have AI components equals a vector of, instead of game entity, this is going to be AI component like this. AI components, AI component. Now if I copy and repeat that 2 more times, now AI components, the next one is going to be the physics. Oh, I forgot to turn off the stack game. That's probably annoying. I'm sorry. Let's see. Physics, components. And then have this will not be AI components, but rather physics component. And then same thing over here. So now we're going to have render component. And you are render component. Now, while we're not game over, we're still going to loop over all these different things, but instead of exactly the same, let's do this different. Like it's going to be very similar to each other, but we're going to loop over like the individual ones. So we're going to have like the AI component in a mutable reference to AI components. And then we can run AI components.update. Cannot AI component. There we go. And so if we replace this twice, then we have AI component. This becomes physics component out of physics components. And then here we have render components out of render components. All right, And so this is this next example here. So the idea is that the code is now going to be in these structs, and they're all going to be together. So we're going to loop through them all in contiguous order. And so it's in the vector, and so it's going to try to keep all the data together in memory. And so it's going to like pull chunks of it out, crunch them, pull chunks of it out, crunch, 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 all the way through. And then we're going to do the same thing to physics, and then eventually rendering. What do I have? Web development and game development. Ooh, did I accidentally leave that tag up? I did. Let me change that. All right. Updated. Web development is gone. Thank you, Just a Guy. All right. So. All right, next up, we're packed data. So say we're doing a particle stream following the advice of the previous section. We've got all of our particles in a nice big contiguous array. Let's wrap it in a little manager class. Okay, so we're gonna have a particle system and a particle. So two structs for us here. Really? Okay, that's cool. Maybe I'll try that later. Struct. Particle. And in here, all we're gonna have is this update method. So we're gonna impl on particle, pub function update, mutable self, and then like, you know, whatever we need to update. So update the movement of the particle. And then we're gonna have the particle system. So struct particle system. And it looks like we're gonna have number of particles that we care about. So num particles. And that's probably going to be some kind of like usize, because it's going to be an index essentially. We're going to have max particles. Which is going to be just some number that we have. So that's probably also a usize, so we can use it when determining what these should be. And then of course the particles themselves. So particles, and this should be max particle. Oh, okay. So this is going to be an actual array here instead of a vector. Because I could do an array, and then I have to say, well, this is going to be particle is what's stored in. But then I have to give it the actual number of particles that are going to be in here. So max particles can't go here. We're going to have to do what they do in this example and make it a constant. So const max particles of type usize, and then set this equals to, you know, they have 100,000 here. That's fine. I'm not learning any specific genre. I'm going through a book called Game Programming Patterns. And it's basically patterns for many different types of genres. And then here is max particles. So this is the size of our array. 2D or 3D? I mean, it doesn't really matter. These are more programming principles and patterns, so it can be applied to any. Programming Mouse, good morning. Are you just trying to port the code into Rust? Yes, exactly. Yesterday we went through the code and converted these into JavaScript, and so today we're converting them into Rust. Okay, so then in our new system, when we instantiate, do we want to like create them? We probably need to like make sure that we create it properly. So having a particle system, let's go ahead and impl on particle system, public function new. We're going to return a particle system, and so let's do num particles. We know what that's going to be. So let's do particle system here. Num particles is going to be 0, so we're starting with that. Now the particles is going to be interesting because we have to now create them and like add it in here. So we have to, I forget like how to do the default with it. Oh, I think it will clone it properly for us. So then we're going to have our particles, which is going to be an array of particle, like that, and then max particles. And you should be yeah, okay, so it's yelling me that I can't copy particle because I didn't say that particle can be copied. So I have to implement that here. But that's pretty easy. I can just derive copy and clone. And now it's able to clone these particles out to max particle size. So now I have an array of 100,000 of particles stored in particles. Do I have a game idea in mind once I learn that? Oh, yes, I do have. The game in mind that I have is probably like an infinite runner. I'm not a game developer per se, so I am interested in like game methods and like how to build games and the technology used. So I'll probably try building like an infinite runner, and we'll just sort of see how this works. I did create an infinite runner originally, and before I learned this, to sort of like just do here's how I do it without, you know, in my naive way. And so now after this, I'm looking forward to like, what did I learn? How can I implement those? Okay, so now in particle system update, hub function update. So we're going to take itself. We're not going to return anything. We're going to loop through all of our particles and run update on it. So for particle in mutable reference to self.particles, we are going to run particle.update. But it turns out we don't actually need to process all the particles all the time. The particle system has a fixed size pool of objects, but they aren't usually all actively twinkling across the screen. So we need to determine which particles are active for us. So then there's going to be an isActive off of a particle here. So do is active and have this be a Boolean. And then we call so then this becomes okay if self dot or actually just self if particle dot is active. So if the particle is active, then go ahead and run the update. But then we can get into some interesting sort of data structure idea here, where in our array, we make sure that we're constantly sorting or keeping the array sorted with all of the active ones at the front of the array, so front of the array, and all the inactive ones at the back of the array. And in that case, we can just track the number of active particles. So over here, we now have num active, which is a usize, because we're probably going to be using this as an index into that array, so it has to be a usize then. When we instantiate this, num active, we're going to set that 0 are active. Then we're going to have an activate particle and a deactivate particle. So pub function activate particle, mute self. And then we're also going to have an index, which is a usize. And so the idea is we're going to take the particle that we want to activate, so it's some index in here, and we're going to swap it with the num active. Oh, we're going to increase num active. So we're going to put it into where num active is. So like just wherever the num active is, we're going to put it into there and then put the num active right behind it. So here, we do have to assert here and then potentially throw an error. Well, errors in Rust are a little bit interesting because there's no like throwing an error. Instead, we're going to have to return a result. And so if we have an error, let's create like just a generic error enum here. Enum errors. So our possible errors, this one will include, let's see, particle already active. So on our result, we have, it's either, so the okay for it is nothing. We don't really care about that. So it's going to be just open parentheses. And then the error for this is going to be an instance of that enum. So errors. And then we're going to swap. So I guess like first we have to check to see, okay, if our index is greater than our num active. We don't really want to do it exactly this way because this is already going to throw an error in C++, and in Rust we have to handle that ourselves. So we're going to do the opposite side. If we want the left-hand side, so smaller index, to be the active, we cannot be checking that. So if the index is less than or equal, probably just less than num active. Some num active. So if that's the case, then we're going to return early an error. And then we're going to pass in what the error is. So errors, particle already active. Now, if we get here, we're going to have to return our OK to make that happy. But before we do that, let's go ahead and actually swap everything. So let our temp equals, it's going to be self.particles of position self.num active. Then particles, self.particles, of position num active self.num active equals, and this is going to be the particle at this position index. So self.particles position index, particles of position index can now be equal to our temp. So temp, and then we want to increment our number of active, because now we have one more active. So self.active plus equals to 1. And then we want to return an OK to make the result happen. What are these errors? Missing field is active and initializer a particle. Ooh, yeah. Okay, so we definitely need this. This is active, false. Trait bound into iterator is not satisfied. Oh, arrays can't go into iterators? So I think I do have to do particles dot iter. Particle is a reference that data cannot be borrowed as mutable. Can I? Is there an iter mute? There is an iter mute. Okay, so that works. And that's all the errors. So everything else is just the warnings because I'm not actually using these. All right, so that's activate particle. Then we're gonna have a deactivate particle too. So pub function deactivate particle. You, come on, keyboard. Mute self, or hands, I guess. Mute self and our index, which is a usize. We're also going to have to return a result here. That and an errors. Okay, so to deactivate a particle, we're doing the opposite. So we're going to be swapping a deactivated particle with the activated particle. Or rather, swap it with the last active particle right before the inactive ones. Okay, so, and then we're going to do the num fewer a little bit earlier. But first of all, we need a particle that is already active. So that means it needs to be on the left side of the array, which means it needs to be smaller. So if index is, it must be smaller than array. So that means we're going to check to see if it's greater than or equal to self.num active. Then we're going to return, and so we can create another error here. So we have particle already active, particle already inactive. So return errors, particle already inactive. So if we get to this point, we're good to go. Now I can add in this OK early, and that will make the compiler happy. So I won't get all those red lines everywhere, which is nice. Okay, so particle system, deactivate particle here. We're taking in that index. We want to deprecate num active immediately because it's also acting as our index. So self.num active minus equals to 1. Then we want to do our entire swap here. So our temp variable is going to hold whatever is in num active after we decrement. So let temp equals self dot particles of position self dot num active. All right, so that holds our particle here. And then we're going to swap into position num active wherever the index is. So self dot particles of self dot num active equals self dot particles of position index. And then self dot particles of position index equals temp. And that's deactivating those particles. So the point of this, and in case you missed yesterday, the idea is that this is cheaper than it might look. And that's specifically because in the games, and I've done like a few visualizations in the past where we ran into this problem, where moving stuff around in memory or like in data is a lot cheaper than like making sure that they're all together, alongside each other. And we did that with like the ECS system when we were trying to put like lots of particles on a screen using my notebook while streaming, where it was having a lot of trouble, but that actually helped it quite a bit. Hot cold splitting. Okay, so the last example here, making our cache happier. Right, because we have some things in cache that happen like quite often, like all the time. And some things that happen only every once in a while, and we're not really going to care about optimizing for those every once in a while cases. So we have this AI component that has the animation, it has the energy, and it has its goal position. Well, it's going to be playing its animation constantly. It's going to be updating its energy constantly, and it's going to be updating its goal position constantly. So if I want to store these in our AI system, here this is. The animation, let's imagine that the animation is just going to be an enum, and therefore in like animation we're just going to be pulling from animation whatever method that is. So we're going to do an enum animations, and maybe we'll have sort of like walk. And so in here we're going to have a animation. It's going to store in animations. We're going to have energy, which is this stores a float, an F32, and a goal position. So goal position, which it looks like this is going to store essentially, they're calling this a vector. It could be a vector of like X and Y, essentially. We can do that. So we can say this is a vector of F32, F32. Actually, I don't think I need one of them. Now it also has these other things in here, and we can add them as well. So we're gonna have so loot type, drop. Okay, so we have our like what our drop is gonna be. So drop, our loot type. So let's create another enum for this because there's going to be only like one type of loot per ones. So loots, loot type. So maybe this is going to be like magic, like maybe sword +1. Sword +1. So our drop is going to be a loot type. We're also going to have like minimum drops and maximum drops. I'm thinking that's like the number of drops they can have at one time. But okay, so min drops is an I32. Max drops is an I32. And chance, like drop chance, I guess. Drop chance is going to be an F32, a percentage. Now this has gotten complex enough that we're definitely going to want some kind of creator, like what is it? The new function, because Rust doesn't have a constructor by default, so we have to create that ourselves with hub function new. And so when this comes in, we're gonna have an animation, which is types animations. We can start with like full energy of whatever that is. Maybe we don't have a goal position. That's gonna come in a little bit later. So we can just give it, or maybe it does, I don't know. Let's instead do drop, which is loot type. The min drops, which is an I32. Max drops is an I32. And drop chance, which is an F32. And we're going to return a AI component. Just to make it a little bit easier to see here. So we want to store all these things internally here. So we're going to say we're going to return an AI component, and animation comes first. Energy. We're going to say that this is 100.0 maybe. Like we start with full energy every single time. Then goal position. Goal position, this is a vector, so we can use the vec macro, and we're just going to say, well, maybe our goal position is 0.0, 0.0. You know, we don't know where it is, so it's just wherever, you know, up left corner, top left corner, since we don't seem to have like its actual location here. Then we're gonna have a drop, so add that in. Drop our min drops, our max drops, and our drop chance. So all of these are gonna go in here and then get returned when we create this. Which means when we use this over here, AI component, this will now be a new. Hand it the animations. So animations. Walk. Our loot's type. I think we have the sword +1. Our minimum drops, we can just say 1. Our maximum drops, maybe it drops it like 5 times over its life. Our drop chance is, let's say like 0.25. That seems like pretty large drop chance. Oh, and I think that's it. So save that, and that creates this. Oh, and we need to replicate this for all these other components. So let's just do that here. And I'll just keep these the same for right now. It doesn't really matter. We have like 3 of the same components. And that's it. No more errors. Perfect. So now what they're suggesting is that we have this loop drop structure here. So if we come back up to our AI struct, we can now have a struct loot drop. Now, they're going to have this friend class AI component. There is no such thing in Rust. So we're just going to have to deal with this on our own. But I don't think it's going to be a problem for us. We're going to have the AI component take ownership of this. So in loot drop here, we are going to drop. Okay, so we need to hold the drop, the min drops, the max drops, and the chance to drop. And so that's this. So everything from this loot type over. So we're just going to cut this out, save it there, and then in loot drop here, we're going to store everything in here. We're also going to have an implement for loot drop. Hub function new. And we're going to take in these. So we have drop, loot type, min drops, max drops, and drop chance. So copy that and put that in here and return a loot drop. And then loot drop, and this is going to be our drop, min drops, max drops, drop chance. Save that to make it look nice. And there's our loot type right there. Or loot drop. Implement loot drop. That's what I wanted. Okay, so with this AI component now, I don't want to store these things. We want to store the animations. We want to store the energy and the goal position. But we're also now going to store the loot. So loot is going to be type. Now, I can't really do a reference to the loot drop. I mean, I could, but I'd run into lifetime problems. And if we're using the game engine like GGEZ, then we're going to run into issues with the lifetimes now being required everywhere and causing us problems. So I'm going to first do it this way, and then maybe if we have time, we can try maybe like a different loot table, which would help out a little bit. So then in our AI component, we've taken all these things like this, but after our goal position, we're not going to have the drop there anymore. We're going to have loot, and that's going to be a loot drop new. And then we're going to pass in these things that we got in. So it's sort of like a pass through for this. So pump function, we're going to do a drop, the min drops, the max drops, and the drop chance. Like that. And so now it stores the drops internally to itself, but it's now also stored in a different location in memory because of this struct over here. And that means when we're walking through, we're not grabbing that data. In Rust, how do we handle polymorphism? We don't. There is no, well, that's not quite true. The trait system allows us to have some polymorphism. And it is nice, but it's not like the same as inheritance and that kind of polymorphism that we can get. And that's it for everything else in here. Now, in the case that we don't want to store the loot drop inside of this component here, what we could do is like have loot drop store maybe internally a vector of all the loots that it could possibly have, and then it will store an index of where that loot information is. So this loot drop is maybe like this specific thing here. We could have another struct. So a struct loots. I don't like all loots. Game loots. Okay, so we're gonna have the loots. We're gonna have the list of all the loots. So all loots, and this is gonna be a vector of loot drop. And that's pretty much all that's going to be stored here. I don't really see any other reason to have anything else. We can have an impl for loots, pub function new. So when we create a new one, we're going to take in the new loot drop. Actually, we'll instantiate with nothing, won't we? And we're going to return a loots. And so we're going to have loots. Which is going to have all loots, which is going to be an empty vector, nothing in it. And then the idea that I have here is we can, when we insert into the loots vector here, we can get the index that we added in, and then return that out. So we can now have a pub function add. Maybe add loot. So mute self, and then the loot, which is a loot drop. And we're going to return a usize, which is going to be the index. So to begin with, it's going to be pretty simple here. We're going to say self.allloots.push, and we're going to push in the new loot. And then we want to return the usize. So we're going to return self.allloots.length -1, because we want the actual index of where we pushed in. And now if we want to get a loot, so pub function get loot, we're going to have a reference to self. And we're going to have the ID of the loot, which is a usize, and we're going to return a reference to a loot drop. Now this should be fine lifetime-wise, because loot should live as long as the game is alive. So we're going to return a reference to self.allloots of position ID. And what that means for us is when we instantiate the game down here, in setup, we need to create our loots. So let loots, like all loots equals loots new. That gives us that. And then in AI components, it's going to have to take those in and then deal with it at that time. So an AI component here, notice we're storing this loot that's loot drop. This can now be the loot index, which is going to be a usize. In new here, we take in all of our drop information, but we're also going to need to take in the loot. So the all loots, which is going to be a reference to loots. And this is going to have to be a mutable reference to loots because we're mutating it. And inside of here, instead of this loot drop new, let's go ahead and I'm going to comment that out so we have it at the end still. I'm going to do a loot index, and we're going to do all loots dot add loot, and then the loot drop. So that's going to be this. So add loot returns a usize, the index of where it goes. So that goes into the loot index. And now if we need it in the update, we can use the loot index to grab the loot from the all loots, and we can pass the all loots in potentially, or like have it available somehow. That's something that we can do. That does mean that we need to potentially add in all loots into update here for it to drop, or maybe there's some other function we can pull out or grab. I don't know how we want to like specifically do that. Maybe we can just have a global function that update can reach out to grab. So it's an option. Add component, all loots. It's not storing loots anymore. We are now storing loot index. Oh wait, no, that's the new. That's fine. All right, and I think that's it. There's not much we can really run here on this one. It's more of like an example of how to write this code in such a way. It's very similar to the ECS system that we have. Oh, and you here, it's yelling at us because we need to pass in all loots and a mutable reference to all loots. So we can do that right here. So a mutable reference to all loots, which means you need to be mutable. And that's it. No more errors. So this code is runnable. It would run, and now it won't do much because we're just sort of running this update and there's no like print lines or anything else, unlike some of those other examples we've done in the past. So would I want to do this? I don't know. I like the entire game entity components that we had before. We don't need them anymore in this example. Like, this is completely useless. We now have everything sort of separated out into their AI components. If I was going to start doing components like this, I would probably reach for an ECS, something like specs and Rust, and use that. And if I didn't feel I needed that for my game, I would probably just stick with game entities and use dynamic dispatch to sort of store an array of all of our components, and then run the update loop over that individually. And it makes coding really, really, really nice. But I think it's going to just depend on how many elements we really need with our system. And it's possible that maybe we do the particle system ourselves because we need those to be in some kind of like nice contiguous array of memory, because we're updating the 100,000 things all at once potentially. That might be something nice to look into for like a stress test of like how many particles can I add with GGEZ while like optimizing the frame rates and the update rate, everything else. But that is this chapter. So I'm going to go ahead and save this code, get this on up to GitHub, and share out the link so that you all can see it and take a look at it. If you want to update, send pull requests in, or just add issues or questions, absolutely. I would love for you to do that. So here's all these changes in here, and implemented, what is this? This is the game locality, data locality. In Rust. How do I have two updates that I haven't pulled down? Push that up. I don't think I've been working on this on another computer. So that's fun. Okay, so push that up. Oh, you know what it was? We got a pull request from the auto GitHub, sort of like fixing Lodash in one of the libraries that we were using, and that that caused our pull to happen. All right, so this is pull push down. I have a bot command bang repo. You could use that to find the link to the code. If you're watching this as a VOD, I'll also have the code in the description of the VOD, where you can go in and look at it there. And so with that, I'm gonna go ahead and put in a marker to end the video.